So in the last video, we learned about graphs in context, and we learned that the slope has units of the units of y divided by the units of x, and the area between the graph and the x-axis has units of x times the units of y. So what we're going to do now is we're going to talk about how calculus plays into all of this. When we were doing this, it was clear that we got geometric shapes, so we could actually find those areas just by using the shape. All right, so what we've got here is a graph that's not linear. This fact, this is quadratic, it's parabolic. So if I give this context, just like we did with the others, time in hours, and let's call this speed in miles per hour. Now, if I wanted to find the miles per hour, which is the acceleration, if I wanted to find the distance traveled, on the last slide, but here, this is not a geometric shape that we know. So if we wanted to find the acceleration, which is the slope, or if we wanted to find the distance traveled, which is like the area, we're going to have to think about this a little bit differently. Now, the idea is if I were to find, like, say, the slope between 0 and 2, that would give me an overall idea of what the acceleration is for that interval. But it's not going to tell me what the acceleration is at, say, 2 itself. If I wanted to find that, what I would have to do is draw lines that pass through 2 points. They get closer and closer together at 2. Now, as those lines get closer and closer together, you can see that that slope starts looking more and more like it's just going to touch at the graph. And when that gets to that point where those points are really close to each other, then the slope would be really, really close to what the acceleration would be at 2. But we can't let those points land on top of each other, because as soon as they do, we can no longer calculate a slope. If you have 0 change in y over 0 change in x, and 0 divided by 0 is not a number. So one thing we need when we're finding these slopes is we need for the points to get as close as possible to each other without actually touching. Now, if I took the same graph and talked about area, so again, y equals negative x squared plus 3x. We're going to call this time in hours. We're going to call this speed in miles per hour. We know that the area underneath this is going to be miles per hour times hours, which is miles. But the shape of that thing is not a geometric figure. So what we would do here is we would take this and break it up into little subintervals, and then we would draw rectangles. Now, there's several ways of doing this. I'm going to draw them from the right-hand endpoint. And then if I add those areas together, that would give me an approximation of what that area is. Now, obviously, it's not perfect. It's not even actually all that good. The first rectangle overestimates. The third rectangle completely underestimates, and the middle one does kind of both. But one of the ways I can make it better is by dividing it into more subintervals and drawing more rectangles. Now, as I keep doing this and making the rectangles finer and finer, go ahead and draw another one so you can see this. If I could draw them like super fine and cap those off with little rectangles all the way down, this is messy, but you get the picture. You see that that area starts to fit better and better and better. So if we wanted to get a really good approximation of the area under the curve, which again represents the distance traveled, we would need a bunch of these little rectangles. In fact, we would want as many of them as we possibly can, but we can't have like an infinite number of rectangles. We can't actually get there. And we can't make the width of the rectangles be 0 because then you can't find an area. So we'd like that width to get as close to 0 without actually reaching it. And we'd like the number of rectangles to get as close to infinity without actually being able to reach it. This is the entire idea behind calculus. We want to find an instantaneous rate of change, a rate of change at a moment. That's this first picture, finding slope, which actually leads to a branch of calculus called differential calculus. It's calculus based on finding slopes. And then we want to be able to find areas under a graph as accurately as possible. And we would need some way of like getting a really good approximation there. This branch, finding the areas, is called integral calculus. And these two branches are the ones we're going to study in AV Calculus AB. The thing that we're going to need to unite these two, and the very first thing we're going to talk about, is something called a limit. And I'm going to let someone else sort of introduce what a limit is to you.